this video is going to briefly review some of the homework that I had asked you to do, where you were looking at the bond energies specifically of a chemical reaction. And the chemical reaction you were looking at is when methane, CH4, reacts with oxygen to produce carbon dioxide and water. So what we need to do is we need to start off by taking a look at what this chemical reaction in terms of structural formulas actually looks like, because once we know the structural formula, we can determine how many of these bonds and the types of bonds we have. So looking at this this chemical equation, CH4, if I were to draw it out, has a tetrahedral structure, in which case I have 4 carbon and hydrogen bonds. I have one here, I have one here, one here, and one here. All right, so looking at my table above on that homework tells me that one CH bond more or less has 413 kilojoules of energy stored in it. And since I have a total of 4 of those bonds, I'm going to multiply that by 4 to have a value of 1632 kilojoules. All right. The next piece is looking at oxygen. It looks like, and I need to make sure that I balance this, I have 2 oxygens. Keep in mind that when I draw out the oxygen has a double bond. Go. And so when I look at my table, I make sure that I look at a oxygen double bonded with another oxygen, and that energy stored in that type of bond is 495 kilojoules. And since I have 2 of them, being that I have 2 O2s, I'm going to multiply that by 2 to have the total energy of 990 kilojoules of energy. Now, keep in mind, when we are breaking these bonds apart, it requires energy. So that means that it's going to require to break every one of the CH bonds 1,632 kilojoules, and to break the oxygen double bonded with oxygens 990 kilojoules, to have a total of 2,642 kilojoules of energy required to break these bonds. All right, so what I'm going to do is move on to the next slide. In the next slide, it gives me what looks like a table, looks like a graph. And so I'm going to place how much energy it takes for each of these types of bonds to break. To break the CH bond, it takes 1,652 kilojoules of energy, and to break those 2 O double bonded with O, it takes 990 kilojoules of energy. So the next piece is the piece of what happens now once you've broken apart every one of these bonds and we have individual atoms. They rearrange themselves to produce CO2 and 2H2O. Again, this is where drawing is absolutely essential. What you're going to notice is that when you draw CO2, you're going to have 2 double bonds of C and O. And so we're going to look at the table, and we recognize that a double bond of C and O is 799 kilojoules of energy, and I have 2 of them. So in that case, it works out to be that I have a total of 1,598 kilojoules of energy that are released. See these atoms as magnetic sort of Lego pieces? Remember, atoms want to reach nirvana, so they will be attracted to each other. It does not take energy to bring them together. It is the most common misconception that making bonds requires energy. It does not. It releases energy. It's like 2 magnets that want to come together, and it's hard to keep them apart, so it releases energy. when they come together. And then we also have two water molecules. So here I have a drawing of my water molecule. And again, I count how many hydrogen-oxygen bonds I have. And in this case, we have 4 hydrogen-oxygen bonds, and I look at my table, and each of those bonds will release 467 kilojoules of energy. And that works out to be a total of 1,868 kilojoules of energy. If I add these two up, this tells me that 3,466 kilojoules of energy were released when these atoms came together. So just to reiterate what I said, when atoms are broken, when chemicals are broken, we need to add energy from the surroundings to break those bonds. However, when bonds are made, energy is released from the system and into the surroundings. So we're going to show that. And we're going to then place those values in these sections. So I had said that 2 CO bonds had a total of 1,598 kilojoules of energy released, and then 4 of the OH bonds released 1,868 kilojoules of energy. If I look at the difference between how much energy went into the system versus how much came out, and you'll notice that you have on the y-axis energy from a low amount of energy to a high amount of energy. You'll notice that the energy increases in the system. Remember, this is the system. And then when bonds are broken, because energy is going in from the surroundings, energy from the surroundings, and then in this side of the graph, you'll notice that the energy is getting less, and the reason is that energy is released from the system and into the surroundings. All right. So overall, if I do find the difference, this reaction is going to have more energy released than is being taken in from the environment. And in fact, it's 824 kilojoules of energy that overall are released. That means that's the difference between these two. This means that this will release more energy than it takes in, and if energy exits or heat exits, this is considered an exothermic reaction. And what we are going to feel is we are going to feel heat. And this is this burning of CH4 is what we actually do in our lab when we burn our Bunsen burners. And we do feel heat from that because more energy is released when those bonds are formed than are taken in.